In the previous discussion, we dealt with limits that describe the behavior of a function f of x as x approaches some real number a, and we were able to write that as the limit of f of x as x approaches a, and we used the variable L to denote that limit. So when f of x, or when x approaches a certain value a, f of x approaches the limit L. So in this lesson, we will be dealing with the behavior of the function f of x when x increases or decreases without bound, meaning there is no specific value of x that we are going to be assigning, but instead x will be increasing or decreasing up to infinity. So if a value of a variable x increases without bound, we write that as x approaches positive infinity because it increases. So it approaches positive infinity. And if the value of x decreases without bound, we write that as x approaches negative infinity. So decrease going towards negative infinity, towards the left. The behavior of the function f of x as x increases or decreases without bound is sometimes called the end behavior of the function. In other words, this is what we call the limit of the function. So that is the end behavior when f of x, or the end behavior of f of x when x increases or decreases without bound. So for example, the limit of 1 over x, this is the curve representing the function y equals 1 over x. And we can see here, x here increases without bound towards the right, and x here decreases without bound towards the left. So when we evaluate or find the limit of 1 over x, as x approaches positive infinity, this curve right here goes to the right indefinitely. So it increases to positive infinity, and what happens to the value of f of x or y is that it will keep approaching the x-axis, which is y equals 0. So therefore, the limit of 1 over x as x approaches positive infinity is equal to 0. On the other hand, when x decreases without bound, going towards the left, approaching negative infinity, the value of y or f of x also approaches 0. It approaches the x-axis. So therefore, still the same, the limit of 1 over x as x approaches negative infinity is equal to 0. So whether it is increasing or decreasing without bound, the limit of 1 over x will always be approaching 0. So for limits or infinite limits at infinity, if the value of f of x increase without bound as x approaches positive or negative infinity, again, f of x will increase without bound. So it will approach positive infinity. As x approaches positive or negative infinity, we write that as the limit of f of x as x approaches positive infinity is equal to positive infinity, or the limit of f of x as x approaches positive or negative infinity is still positive infinity. But if the values of f of x decrease without bound, as x either approaches positive or negative infinity, then we denote that as the limit of f of x as x approaches positive infinity is negative infinity, or the limit of f of x as x approaches negative infinity is equal to negative infinity. So we have here illustrations of the end behavior of different polynomials in the form x to the power of n. This is in the form x to the power of n, We're in the first example here, n is equal to 1, n is equal to 2, n is equal to 3, and n is equal to 4. So for y equals f of x, or y equal to x rather, the curve is a line inclined to the right intersecting the origin. The slope is positive. So as we can see here, when x increases without bound, the value of y will also increase without bound. Therefore, the limit of x as x approaches positive infinity is also positive infinity. On the other hand, when x decreases without bound, so it now goes to the left, negative infinity, the value of y will also be decreasing. So that's directly proportional. So that's negative infinity. So the limit of x as x approaches negative infinity is also negative infinity. As for y equals x squared now, as x approaches, as x increases without bound towards the left, or right rather, positive infinity, the value of y also increases, because this will increase here indefinitely as the value of x increases. So that would also be positive infinity. The limit of x squared as x approaches positive infinity is also positive infinity. But if the value of x decreases without bound towards the left, negative infinity, the value of y is still increasing. So that is still directed to positive infinity. So the limit of x squared as x approaches negative infinity towards the left is still positive infinity. For x cubed, it's a different curve. When x approaches positive infinity, going towards the right, the value of y also increases to positive infinity. You see there, it's going upward. But when x approaches negative infinity, going towards the left, the value of y also decreases, negative infinity. So the limit of x cubed as x approaches positive infinity is positive infinity, and the limit of x cubed as x approaches negative infinity is still negative infinity. For x to the power of 4, it's similar to x squared, wherein the limit when x approaches positive infinity, y will also be approaching positive infinity, and when x approaches negative infinity, y will also be approaching positive infinity. So here. So the pattern is repeating actually. When you increase 1 here, x to the power of 5, the curve would be something like this, just like x cubed. If it's now x to the power of 6, it would be similar to x to the power of 4. It would still be facing upward. If it's x to the power of 7, again, it would be similar to like this. And if it's x to the power of 8, it would be facing upward still. But if it's negative x squared, when we write y equals negative x squared, this curve will be facing downward. And so if we are asked to evaluate the limit of x squared, negative x squared rather, as x approaches positive infinity, our limit would be the negative infinity because it's going downward. And if you're asked to find the limit of x squared, negative x squared, as x approaches negative infinity, our answer would still be negative infinity because it's going downward again. If we're asked to find if the curve is y equals negative x cubed, it would be a mirror image of this curve right here. So the curve would look like this. And so if we're asked to find the limit of negative x cubed as x approaches positive infinity, our limit is negative infinity. And the limit of negative x cubed as x approaches negative infinity would be positive infinity because y is increasing. For us to find y equals negative x to the power of 4, the curve would be facing downward. So still the same with this one, wherein the limit of negative x to the power of 4 as x approaches positive infinity is negative infinity, and the limit of negative x to the power of 4 as x approaches negative infinity is still negative infinity. So this is special cases now for polynomials with these exponents.